Picture this. You drop a glass on the kitchen floor, and it shatters into 1,000 pieces. Glass flies everywhere. The sound echoes through the room, and suddenly your peaceful morning is interrupted by the need to find a dustpan. Now, here's a question that might seem obvious at first, but stick with me. Why doesn't that glass ever spontaneously reassemble itself? Why don't those scattered fragments suddenly leap back together, forming a perfect, unbroken glass that floats gracefully back up to your hand? Your first instinct might be to say, well, that's just not how the world works. And you'd be absolutely right. But here's the thing. The fundamental laws of physics don't actually forbid this from happening. Newton's laws of motion work perfectly fine in reverse. Einstein's equations don't care which direction time flows. Even the bizarre rules of quantum mechanics are largely indifferent to whether time moves forward or backward. So if the deepest laws of nature are essentially time-symmetric, why does our everyday experience feel so dramatically one-directional? Welcome to one of the most profound puzzles in all of science, the arrow of time. I'm about to take you on a journey through one of physics' greatest mysteries, a mystery that touches everything from why you can remember yesterday but not tomorrow, to why the universe itself seems to have a built-in sense of direction. And fair warning, by the end of this exploration, you might never look at a melting ice cube the same way again. But before we dive deep into the physics, let me tell you why this matters. The arrow of time isn't just some abstract concept that physicists debate in ivory towers. It's the reason your coffee gets cold instead of spontaneously heating up. It's why photographs capture moments from the past, not glimpses of the future. It's why you age forward through your life, rather than Benjamin Buttoning your way backward. In essence, it's what makes our entire experience of reality possible. Now, I know what some of you might be thinking. Obviously, time moves forward. I don't need a physics degree to know that. But here's where things get fascinating. The fact that we all intuitively know time has a direction is actually part of the mystery. Our brains are so wired to expect temporal order that we rarely stop to ask why this order exists in the first place. Here's what we're going to explore together. First, we'll unpack exactly what physicists mean when they talk about time's arrow, and why it was such a shocking discovery that the laws of physics don't naturally provide one. Then we'll dive into the real culprit behind time's direction, entropy and the second law of thermodynamics. We'll see how this connects to the biggest arrow of all the expansion of the universe itself. And finally, we'll explore how your very ability to form memories and perceive the flow of time emerges from these same physical principles. The story begins in 1927 with a British astrophysicist named Arthur Eddington, who first coined the phrase arrow of time. Eddington was grappling with a profound contradiction that had been bothering physicists for decades. On one hand, the equations that describe how particles move, how energy flows, and how forces interact are almost entirely reversible. Run them backward, and they work just as well. On the other hand, the world we actually live in is filled with irreversible processes, things that happen in one direction and never spontaneously reverse. Think about it this way. If you filmed a movie of planets orbiting the sun and played it backward, the physics would still make perfect sense. The gravitational forces, the conservation of energy, the angular momentum, everything checks out whether time flows forward or backward. But if you filmed a movie of an egg breaking and played it backward, you'd immediately know something was wrong. The sight of egg fragments spontaneously leaping together to form a perfect shell would violate everything we know about how the world works. This is the heart of the mystery. The microscopic laws that govern individual particles don't distinguish between past and future. Yet somehow, when you put trillions upon trillions of these particles together, a clear sense of temporal direction emerges. It's like having a crowd of people who are all perfectly willing to walk in any direction, yet somehow the entire crowd always moves in the same way down the street. The answer, it turns out, lies in a concept that might sound familiar but is probably more profound than you realize: entropy. Now, entropy is one of those scientific terms that gets thrown around a lot, often incorrectly. You might have heard it described simply as disorder or randomness. But that's not quite right. and the real definition is both more precise and more mind-bending. Entropy is actually a measure of the number of ways you can arrange the microscopic components of a system while keeping its macroscopic properties the same. Let me give you an example that'll make this crystal clear. Imagine you have a room with all the air molecules crowded into one corner. There's basically only one way to arrange all those molecules to achieve this configuration. They all have to be in that corner. But now imagine the air spread evenly throughout the room. There are countless different ways to arrange those same molecules while still maintaining this even distribution. Each individual molecule could be in any number of positions, as long as the overall density remains uniform. The state with more possible arrangements, the evenly distributed air, has higher entropy. And here's the crucial insight. Systems naturally evolve towards states with higher entropy simply because there are more ways to be in those states. It's not that there's some force pushing things toward disorder. It's that high entropy states are vastly more probable than low entropy states, purely as a matter of statistics. This is why that broken glass never spontaneously reassembles. The shattered state represents an enormously higher number of possible arrangements than the intact glass. The molecules could be scattered in countless different patterns and still constitute broken glass, but there's essentially only one way to arrange them to form the original unbroken glass. The probability of random thermal motion spontaneously organizing all those molecules back into perfect crystal structure is so astronomically small that it would never happen in the lifetime of the universe. But here's where the story gets even more interesting. The second law of thermodynamics, which states that entropy always increases in isolated systems, gives us our first real arrow of time. Unlike Newton's laws or Einstein's equations, the second law is fundamentally directional. It tells us that systems evolve from low entropy states to high entropy states, never the reverse. This provides a way to distinguish between past and future that doesn't exist in the fundamental equations of motion. Think of entropy as time's fingerprint. If you're shown two photographs of a system, one with lower entropy and one with higher entropy, you can immediately tell which came first. The ice cube in your drink has lower entropy than the cold water it becomes. The neat stack of papers on your desk has lower entropy than the scattered mess after a gust of wind. The concentrated fuel in your car's tank has lower entropy than the dispersed exhaust gases it becomes. This is why Eddington famously said, "Let us draw an arrow arbitrarily." If, as we follow the arrow, we find more and more of the random element in the state of the world, then the arrow is pointing towards the future. If the random element decreases, the arrow points towards the past. Entropy increase doesn't just correlate with our experience of time's passage. It may actually be what creates that experience in the first place. But this raises an even deeper question. If entropy always increases, why was it ever low to begin with? Why didn't the universe start in a maximum entropy state where nothing interesting could ever happen? To answer that, we need to zoom out from broken glasses and melting ice cubes to consider the biggest arrow of time of all the evolution of the entire cosmos. The answer lies in what might be the most dramatic beginning imaginable, the Big Bang. About 13.8 billion years ago, everything we can observe in the universe was compressed into an unimaginably small, hot, and dense point. Now, you might think that such an extreme state would represent maximum entropy, maximum disorder, but from a gravitational perspective, this couldn't be further from the truth. Here's the counterintuitive part. A universe filled with smoothly distributed matter and energy is actually in an extremely low entropy state when gravity is involved. Think about it this way. If you have a perfectly uniform soup of particles spread evenly throughout space, gravity will naturally want to pull them together. The high entropy state, gravitationally speaking, would be one where all that matter has collapsed into dense clumps, stars, planets, black holes, and other cosmic structures. So when the universe began as this smooth, uniform expanse, it was essentially starting with a cosmic deck of cards that was perfectly shuffled and organized. And just like those cards will naturally become more mixed up over time, the universe has been evolving toward higher entropy states ever since. The formation of galaxies, stars, and planets isn't a move toward order, it's actually entropy increasing on a cosmic scale. This gives us what physicists call the cosmological arrow of time. The expansion of the universe provides a built-in direction that aligns perfectly with the thermodynamic arrow. As space itself stretches and matter spreads out, the overall entropy of the cosmos increases. The universe is literally growing older and more disordered with each passing moment. But here's where the story takes a fascinating turn towards something much more personal: your own consciousness and memory. The way you experience time, remembering the past but not the future, feeling like you're moving from known moments toward unknown ones, isn't separate from these physical processes. It's actually a direct consequence of them. Every time you form a memory, your brain has to physically change. Neurons fire, synaptic connections strengthen, proteins are synthesized. All of these processes require energy expenditure and create irreversible changes in the microscopic structure of your brain. In other words, memory formation increases entropy. You can only remember events that have already left their entropic footprint in your neural networks. This creates what's known as the psychological arrow of time. You remember eating breakfast this morning because that experience caused specific patterns of neural activity that left lasting changes in your brain structure. But you can't remember what you'll have for breakfast tomorrow because those neural changes haven't happened yet. They can't happen until the actual experience occurs and drives the entropy increasing processes of memory formation. It's a beautiful and somewhat mind-bending realization. Your subjective experience of time's flow emerges from the same thermodynamic principles that govern melting ice cubes and cooling coffee. Your consciousness isn't separate from the physical universe. It's woven into the very fabric of time's arrow. But the quantum world adds yet another layer to this story. At the smallest scales, individual particles exist in strange superposition states, able to be in multiple places or conditions simultaneously. These quantum systems are governed by equations that are perfectly time-reversible. A quantum particle evolving forward in time follows the exact same mathematical rules as one evolving backward. The magic happens when these microscopic quantum systems interact with their environment. Through a process called decoherence, quantum superpositions collapse into definite states. But here's the key: this collapse is irreversible. Once a quantum system becomes entangled with its surroundings, which happens almost instantly for anything larger than isolated particles, the information about its original superposition state spreads out into the environment and becomes effectively impossible to recover. Imagine a photon passing through a double slit. Initially, it exists in a quantum superposition, simultaneously taking both paths. But the moment it interacts with air molecules, detector screens, or even stray electromagnetic fields, this delicate superposition collapses. The quantum information doesn't disappear, it becomes entangled with countless environmental degrees of freedom, spreading out in a way that's practically irreversible. This quantum decoherence provides a microscopic foundation for the arrow of time. Even at the smallest scales, where individual particles obey time-symmetric laws, the interaction with complex environments creates an effective direction to time. Information flows from organized quantum states to increasingly entangled mixed states, another manifestation of entropy increase, but now at the quantum level. The implications are staggering. The same quantum processes that allow particles to tunnel through barriers and exist in multiple states simultaneously also contribute to the irreversible flow of time we experience. Every measurement, every interaction, every moment of quantum decoherence adds to the universe's growing store of entropy and pushes time's arrow forward. This brings us to one of the most profound realizations in modern physics. All the different arrows of time we observe, thermodynamic, cosmological, psychological, quantum, are intimately connected. They all point in the same direction because they all arise from the same fundamental asymmetry in the universe's initial conditions. The universe began in a very special low-entropy state and has been evolving toward higher entropy ever since. This evolution manifests as expanding space, forming structures, increasing disorder, quantum decoherence, and the flow of information from past to future. Your morning coffee cools down, your memories accumulate, and the universe ages all for the same underlying reason. But this raises what might be the deepest question of all. Why did the universe start in such a special low-entropy state? This is where our current understanding hits its limits. Some theories suggest that what we call the Big Bang was actually just one event in a larger, eternal multiverse where different regions have arrows of time pointing in different directions. Others propose that the laws of quantum gravity themselves somehow select for low-entropy initial conditions. The honest answer is that we don't know yet. The origin of time's arrow remains one of the most profound, unsolved puzzles in all of science. But what we do know is remarkable enough. The direction of time emerges from the statistical behavior of matter and energy, the expansion of space itself, and the fundamental nature of information and measurement in quantum systems. Every tick of your clock, every beat of your heart, every thought in your mind is part of this cosmic story. A story written in the language of entropy, unfolding across billions of years, connecting the smallest quantum fluctuations to the largest structures in the observable universe. And that brings us to something that might blow your mind. Causation itself, the very notion that events cause other events, is actually an arrow of time in disguise. When we say that lighting a match causes a fire, or that pressing the gas pedal causes a car to accelerate, we're describing something that feels so fundamental to reality that we rarely question it. But dig deeper, and you'll find that causation is really just entropy increase wearing a clever disguise. Here's what I mean. When you light that match, you're taking a highly organized chemical system, the match head with its carefully arranged molecules of sulfur and potassium chlorate, and triggering a reaction that disperses that organization into heat, light, and scattered combustion products. The cause is always the lower entropy state, and the effect is the higher entropy result. You never see fires spontaneously organizing themselves into unburned matches, just like you never see effects preceding their causes. This connection runs so deep that some physicists argue our entire concept of free will and agency emerges from thermodynamics. When you decide to pick up your coffee cup, you're creating correlations between your brain state and the cup's position. But this correlation-building process requires energy expenditure in your neurons, which increases entropy. In a very real sense, your ability to influence the future to be a cause rather than just an effect depends on the same entropic processes that make ice cubes melt. Now, let me take you even deeper into this rabbit hole with something called the epistemic arrow of time. This is the observation that we have records of the past, but never of the future. Think about all the ways we preserve information about what's already happened. Photographs, fossils, impact craters, written documents, even the scars on your hands from childhood accidents. These are all low entropy configurations that persist through time, carrying information about past events. But here's the fascinating part. Creating any record requires an entropy increase. When light from the past hits a photographic film, chemical reactions occur that permanently alter the film's molecular structure. When your brain forms a memory of reading this sentence, proteins are synthesized and neural pathways are modified. When a meteor creates a crater, the organized kinetic energy of the meteor is dispersed into heat and permanently rearranged rock formations. This is why we can have archaeological evidence of ancient civilizations, but never archaeological evidence of future ones. The past leaves traces because those traces represent entropy-increasing processes that have already occurred. The future can't leave traces because the entropy-increasing processes that would create those traces haven't happened yet. But wait, there's another twist to this story that gets even stranger. In rare subatomic processes involving what's called the weak nuclear force, physicists have discovered tiny violations of time reversal symmetry. Certain particle interactions behave slightly differently when run forward versus backward in time. It's as if the universe has a microscopic preference for one temporal direction built right into the fundamental forces. However, here's the catch. These violations are incredibly small and don't seem to contribute meaningfully to the arrow of time we experience in everyday life. They're like finding a few grains of sand that naturally roll uphill while watching an entire beach of sand flow downward. Interesting from a fundamental physics perspective, but not the driving force behind why your coffee gets cold or why you remember yesterday. The real action happens when we zoom out from individual particles to complex systems with many degrees of freedom. This is where information theory enters our story. Modern physicists increasingly view the arrow of time through the lens of information, how it flows, how it gets mixed up, and how it becomes impossible to unmix. Imagine trying to unscramble an egg. The problem isn't that the laws of physics forbid it in principle. If you could track every single protein molecule and apply precisely the right forces at precisely the right moments, you could theoretically reverse the scrambling process. The problem is information. Once those molecules have mixed and dispersed, the information about their original configuration has become so spread out and entangled with their surroundings that reconstructing it would require knowing more about the system than is practically possible to measure. This is what physicists mean when they talk about information becoming thermalized or scrambled. The information doesn't disappear. Conservation laws prevent that, but it becomes so mixed up with other information that it might as well be lost forever. It's like trying to unscramble a jigsaw puzzle where all the pieces have been scattered across an entire city. The pieces still exist, but finding and reassembling them would take longer than the age of the universe. This information theoretic perspective reveals something profound about the nature of irreversibility. The processes we think of as irreversible breaking, mixing, burning, aging aren't truly impossible to reverse. They're just so improbable that they never happen in practice. The arrow of time isn't a fundamental law like gravity or electromagnetism. It's a statistical phenomenon that emerges when you have systems with enormous numbers of particles and enormous numbers of possible configurations. And this brings us to perhaps the most mind-bending realization of all. The arrow of time might not be universal. In distant regions of a hypothetical multiverse, or in different epochs of cosmic history, the statistical conditions that give rise to our arrow of time might not hold. There could be realms where entropy decreases, where effects precede causes, where broken glasses spontaneously reassemble, and people age backward from death to birth. Of course, conscious observers like us couldn't exist in such regions. Our brains depend on the entropy-increasing processes of memory formation and information processing. We can only find ourselves in parts of space and time where the arrow points in the direction that allows complex structures like stars, planets, and thinking beings to exist and persist. This is where the story comes full circle to the cosmic perspective. The arrow of time isn't just about physics, it's about the conditions necessary for complexity, consciousness, and life itself. We exist in a universe that began in a low-entropy state precisely because that's the only kind of universe capable of producing observers who can contemplate these questions. The expansion of space, the formation of structures, the evolution of complexity, the emergence of life, the development of consciousness, and your ability to sit here pondering these ideas, they're all connected threads in the same cosmic tapestry. Time's arrow isn't just the backdrop against which your life unfolds, it's the very condition that makes your existence possible. But here's something that might surprise you. Despite all this talk about entropy and irreversibility, the universe is still full of apparent contradictions to time's arrow. Every time a seed grows into a tree, or an embryo develops into a complex organism, or your body repairs a wound, it seems like entropy is decreasing, like order is spontaneously emerging from disorder. The key word there is apparent. These biological processes don't violate the second law of thermodynamics because they're not isolated systems. A growing tree absorbs energy from sunlight and nutrients from the soil, using that energy to build complex structures while generating heat and waste products. The tree's entropy decreases locally, but the total entropy of the tree plus environment system increases. The same is true for every living thing. We're all entropy, decreasing islands in an entropy, increasing ocean. This reveals something beautiful about life itself. Living things are essentially machines for locally reversing entropy's flow, creating pockets of organization and complexity by borrowing energy from their surroundings. We're temporary eddies in the river of time, swirling upstream for a brief moment before rejoining the inexorable flow toward higher entropy. And that temporary nature is crucial. Nothing can fight entropy forever. Stars eventually burn out, organisms eventually die, and even the most complex structures in the universe will eventually succumb to the relentless increase of disorder. The ultimate fate of the universe, according to our current understanding, is a state of maximum entropy called heat death, a cold, dark, uniform soup where no further interesting processes can occur. But don't let that cosmic perspective make you melancholy. The fact that entropy increases doesn't make life meaningless, it makes life precious. Every moment of consciousness, every experience of beauty, every act of love and creativity exists because the universe is still far from equilibrium, still rich with the potential for complexity and change. You are, quite literally, a temporary arrangement of atoms that has learned to contemplate its own existence. Your thoughts, your memories, your sense of moving through time from past to future, all of these emerge from the same physical processes that govern cooling coffee and expanding galaxies. You're not separate from the universe, you're one of the ways the universe has found to experience itself. The arrow of time doesn't just explain why glasses break and don't spontaneously repair themselves. It explains why you exist at all, why you can remember reading this sentence, and why you have any experience of temporal flow whatsoever. It connects the smallest quantum interactions to the largest cosmic structures, revealing a universe that's not just a collection of particles bouncing around, but a vast, interconnected system exploring all possible ways of arranging matter, energy, and information. And here's where the story takes a turn that might make your head spin. Everything I've just described about entropy, information, and the arrow of time has profound implications for how we think about the nature of reality itself. Because it turns out that the fundamental building blocks of our universe, space, time, matter, and energy might all be emergent properties of something even more basic, the flow of information through quantum systems. Consider this. When physicists peer into the quantum realm with their most sophisticated experiments, they find something deeply unsettling. The act of measurement itself seems to play a fundamental role in determining reality. Before you measure a quantum particle's position, it doesn't have a definite location. It exists in a ghostly superposition of all possible positions simultaneously. But the moment you observe it, this superposition collapses into a single definite state. Now, here's the mind-bending part. This collapse is irreversible. Once you've measured that particle and collapsed its wave function, you can't unmeasure it. The information about its original superposition state has been irretrievably scrambled into the environment. And this process, the irreversible flow of quantum information from organized, coherent states to disorganized, entangled states, might be the deepest source of time's arrow. Think of it this way. Every interaction in the universe, from photons bouncing off surfaces to neurons firing in your brain, involves quantum measurements at some level. Each measurement destroys some quantum coherence and spreads information into the environment in an irreversible way. The universe is essentially a vast information processing system, constantly measuring itself, constantly collapsing quantum possibilities into classical realities, and constantly pushing time's arrow forward through this endless cascade of irreversible information flow. This perspective transforms our understanding of what the universe fundamentally island. It's not just a collection of particles moving through space and time, it's a computational process working through all possible quantum states and selecting specific realities through the mechanism of measurement and decoherence. Every moment of your existence represents the universe making countless quantum decisions about what becomes real and what remains merely possible. But here's something that will really make you question everything you think you know about time. The mathematics of quantum mechanics suggests that the wave function of the universe, the complete quantum state of everything that exists, doesn't actually evolve in time at all. From the perspective of the universal wave function, all moments that ever were or ever will be exist simultaneously in a timeless mathematical structure. This is where physics starts to sound more like philosophy or even mysticism. If the fundamental description of reality is timeless, then where does our experience of temporal flow come from? The answer might be that time isn't something we move through. It's something we construct from the patterns of correlation and information flow within the universal quantum state. Imagine reality as a vast, multidimensional tapestry, where every thread represents a quantum degree of freedom. From outside this tapestry, you could see all of it at once, past, present, and future, woven together in a single eternal pattern. But from inside the tapestry, embedded within the weave itself, you can only perceive the local correlations between nearby threads. The pattern of these correlations creates your sense of being at a particular moment, moving from one configuration to the next. Your memories aren't records of moments you've traveled through. They're patterns of correlation within your current quantum state that happen to encode information about different regions of the timeless tapestry. Your sense of anticipating the future isn't about moving towards something that doesn't yet exist. It's about the statistical correlations in your current state that make certain future patterns more likely than others. This might sound abstract, but it has concrete implications for how we think about identity and consciousness. If time is emergent rather than fundamental, then the you that existed 5 minutes ago isn't someone you used to be. It's a different pattern of correlations within the same timeless quantum structure. The continuity you feel between past and present selves is a story your brain tells itself based on the information patterns encoded in your current neural state. But don't worry, this doesn't make your experiences less real or meaningful. If anything, it makes them more profound. You're not just a temporary arrangement of atoms stumbling through time. You're a self-organizing pattern of information within the universe's quantum computation, a way for the cosmos to experience and understand itself from within. And here's perhaps the most beautiful implication of this view. Consciousness itself might be time's ultimate arrow. Every moment of awareness, every subjective experience, every qualia-rich instant of seeing color or feeling emotion represents the universe making irreversible quantum measurements on itself. Your consciousness isn't just along for the ride in time's forward flow, it might actually be one of the mechanisms that creates that flow. When you see a sunset, your visual cortex is performing countless quantum measurements on the photons hitting your retina. When you feel happy or sad, your neurons are collapsing quantum superpositions into specific patterns of electrical activity. When you make a decision, you're selecting one branch from the quantum tree of possibilities and making it real through the irreversible process of neural computation. This suggests something extraordinary. Conscious observers might play a fundamental role in the universe's evolution, from quantum possibility to classical reality. We're not just witnesses to time's arrow, we're participants in its creation. Every moment of consciousness adds to the universe's growing store of actualized information, pushing the cosmic story forward from quantum uncertainty to classical definiteness. The implications stretch even further when we consider the possibility of other conscious observers throughout the universe. Every alien mind, every artificial intelligence, every complex information processing system anywhere in the cosmos would be participating in the same grand project, converting quantum potential into actual experience, transforming the possible into the real through the irreversible act of observation and measurement. And this brings us to perhaps the most profound question of all. What happens when the universe reaches maximum entropy, when all the stars have burned out and all the black holes have evaporated away? Will time's arrow simply stop? Will the universe settle into a timeless, unchanging state where nothing interesting can ever happen again? Maybe not. Even in the deep future, as the universe approaches its maximum entropy state, quantum fluctuations will continue to create tiny pockets of order. Virtual particles will still pop into existence and annihilate. Information will still flow through quantum fields. And perhaps, in ways we can't yet imagine, new forms of consciousness might emerge, minds capable of experiencing time's arrow, even in a universe that seems to have forgotten how to change. The arrow of time isn't just a feature of our current cosmic epoch. It might be an eternal aspect of any universe capable of supporting information, complexity, and consciousness. As long as there are quantum measurements to be made, correlations to be formed, and information to flow from possible to actual, time will have its direction. So the next time you watch that glass shatter on your kitchen floor, remember you're witnessing one small moment in the universe's greatest ongoing project, the transformation of quantum possibility into classical reality, the conversion of what could be into what island. Your very act of observing that broken glass, of forming memories about it, of contemplating its irreversible journey from order to disorder, makes you a collaborator in time's grand adventure. The arrow of time doesn't just explain the world around us, it reveals our place within the cosmic story as conscious participants in the universe's endless exploration of what it means to exist, to change, and to become